Today we're going to explore how to do calculations that are the result of combustion analysis. So when a chemical is burned, it produces carbon dioxide and water normally, if it's a hydrocarbon. Here we have some data that would have been obtained if you did a combustion analysis on something that has carbon, oxygen, and potassium. And what we find is that the molecule had 0.104 moles of potassium, 0.052 moles of carbon, 0.156 moles of oxygen. So the normal procedure is to divide by the lowest number in the mix to get hopefully integer values, which we did in this case. So there are 2 potassium atoms, 1 carbon atom, and 3 oxygen atoms. The 1:3 ratio of carbon-oxygen would suggest carbonate, and then potassium carbonate is what you get. So it helps to also recognize your polyatomic ions. If you know what carbonate is, then you'll see right away that this is a carbonate anion. In B, the compound has 5.28 grams of tin and 3.37 grams of fluorine. So instead of starting from moles, now they're starting us off with grams of the substance. So we have to divide by the molar masses of the elements to give us mole values. So these are units of moles. And the lower of these two numbers is this one, 4.44 times 10 to the minus 2. Divide both of them by that number, and you get the ratio 1 to 3.988. Now this sometimes disturbs students because it's not a nice perfect round number, but that is more consistent with what you get in real-world experiments. In a real-world experiment, you'll get very close to that integer value, and that will tell you that it's actually a 1 to 4 ratio. On occasion, though, and you're going to see that in another problem, you might get a number that's close to an integer value, but not close enough for you to round it off. And you have to exercise your judgment as to whether or not it is within experimental error. And then sometimes, in a real-world experiment, you might have to redo the experiment to make sure that you get closer and closer to the true value. Very often, your real-world experimental values will go above and below the true value, and then when you average it out, you get closer to what the true value is, unless you have some kind of systematic error in your experimentation. In part C, we have 87.5 grams of nitrogen, 12.5 grams of hydrogen, divided by the molar mass of the two elements. I've neglected to put in the units just to show the calculation more quickly, but in this case, this is one time where I would encourage you to leave out the units, because it's the same sort of procedure each time, and you're looking for a ratio. Final answer is not going to have any units. It's just going to be the formula of a molecule. So we know that this is how it works out, and you can neglect writing the units here without creating a great scandal. At any rate, the ratio of moles is 6.2 to 12.4. When you divide by 6.2, you get a 1 to 2 ratio, which suggests NH2. So that's not an actual molecule. It's just that's the empirical formula. That's the molecule's formula in lowest terms. Remember what empirical formula means. In 349, they're doing an experiment where they're burned toluene. I'll read you what the question says. It says, toluene? No, okay, yeah. Styrene, not toluene. Styrene, a compound substance used to make styrofoam cups in installation. It contains 92.3% carbon and 7.7% hydrogen by mass. It has a molar mass of 104 grams. This question comes from your textbook, Brown and others, 10th edition. When you divide by the molar masses of each of the elements involved, you get 7.68 moles of carbon and 7.64 moles of hydrogen. So you see again, the typical real-world results. It's a 1-to-1 ratio, pretty close. You can see that they're not at all far away within reasonable experimental error. So the empirical formula is CH. Now, if you add the molar masses of carbon and hydrogen, you get 13, roughly 13. I didn't bother to get it right down to the exact value, but that's what it is. It's roughly 13. And when I divided 104 by 13, I got 8. Therefore, the formula of the monomer to make styrene, or polystyrene, is the styrene monomer. It's this molecule portrayed here, and it has the formula C8H8. So how did you find that out? 8 times the empirical formula. C8H8, that's how you get that. On the next one, 349B, it's on the next board. We are asked,
caffeine, a stimulant found in coffee, contains 49.5% carbon, 5.15% hydrogen, 28.9%, let's reread that. 49.5% carbon, 5.15% hydrogen, 28.9% nitrogen, and 16.5% oxygen by mass, and has a molar mass of about 195 grams per mole. So when it gives you the molar mass, then you know that you have enough information to find out the true formula. If they don't give you the molar mass, you'll have to stop at empirical formula. So let's see, we do the normal procedure to find the empirical formula. We assume 100 grams, so you can turn all those percentages into gram amounts, divide by the molar masses of each of the elements involved. You get a mole ratio of each one of the elements involved, and then you divide it by the smallest number in that ratio, which is 1.03 in this case, and you get integer values, 4, 5, 2, 1. So the empirical formula of caffeine is C4H5N2O. You add up all these quantities to find the molar mass, or the empirical formula weight, as it's written here. That's why I wrote EFW, empirical formula weight. And you get 97.0965. But they tell us in the question that the actual formula weight is 195. So if you take 195 grams per mole, which is the molecular mass, and you divide it by the empirical formula weight, you get 97.0965 grams per mole. You'll get roughly 2. So that means you take 2 times that formula, which is C4H5N2O, and you get the actual formula of caffeine, which is C8H10N4O2. And if you look up caffeine, it looks like this, just for the sake of interest. It's a xanthine, trimethylxanthine. It's also known as 1,3,7-trimethylxanthine. And they number it this way: 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, 7, 8, 9. So like you see now, 1, 3, 7. These are methyl groups. And that's that formula. So you can't find the structure of caffeine from these calculations, but you can certainly find the formula. To find the structural characteristics, you have to use an NMR and an IR, or maybe derivatization experiments, the way they used to do before the invention of the machines that they use now to characterize unknown molecules. So this is also known as caffeine. Okay, the next problem that we're going to do is a combustion analysis problem where we're given data for the combustion of toluene. This is 351 in the book. And it's our first experiment where we have real-world data. So it'll give you a taste of what it's like to do an experiment, a real-world experiment. It says combustion analysis of toluene, a common organic solvent, gives 5.86 milligrams of CO2 and 1.37 milligrams of H2O. If the compound contains only carbon and hydrogen, what is its empirical formula? So we're going to start by making the problem a little easier to solve. We're going to make an assumption. We're going to multiply our experimental values by 1,000. That's not going to change the result in any way. All it does is makes it easier to work with the numbers because we're now working with grams. So we assume, this is number 351A,
assume a sample that is 1,000 times bigger. Work with grams instead of milligrams. All right, so when you do a combustion of an unknown substance with, I don't know how many carbons, and I don't know how many hydrogens, so I'm going to put variables there, CX, HY. Don't know what the composition is. You need oxygen and water are produced. Carbon dioxide and water are produced. And we're told that 5.86 milligrams of carbon dioxide is produced, but if we turn it into grams to make the calculation a little bit easier, we're also told 1.37 grams of water is produced, which we also, it was milligrams, we switched it to grams. We divide by the molar mass of carbon dioxide. I also recommend to my students always to write in the margins of their not their textbook, of their notebook, the molar mass of carbon dioxide and the molar mass of water, just because you use that those numbers so often that you could save yourself some time just by memorizing that value. Molar mass of carbon dioxide and the molar mass of water, 18.01528. Is that right? Yeah, 18.01528 grams per mole. Now, this will give you the moles of carbon dioxide produced, and that will give you the moles of water produced. And the numbers are 1.33152. Notice how I keep all the decimal places during my calculation. Moles of CO2 and C. Sometimes students have a problem with that. If you have that many moles of CO2, you're also going to have the same number of moles of C, because for every molecule of CO2, you have one atom of carbon. Okay, so once you find the moles of carbon dioxide, you've also found how many moles of carbon were in the original molecule that you burned. Because where is all the carbon coming from? Coming from here. For water, the result is 7.604 6556 times 10 to the minus 2 moles of water. But remember that water has a 2-to-1 ratio of hydrogen atoms per every mole of water, so you can say times 2 moles of hydrogen for every 1 mole H2O, and the result is that you have 1.520 93112 times 10 to the minus 1 moles of hydrogen. Now, we have the mole ratios. Let's rewrite them here neatly and use their normal calculation. That'll be 0.133152162 moles of C and 0.152093112 moles of H. Divide by the lower one of the two, which is the 0.133. Divide by 0.133. I didn't rewrite the whole number, but I did use the whole number, and you'll get the ratio 1 to 1.14. And this is where some people will get stumped. They'll say, well, some people might be tempted to say, well, that's 1.14, that's close to 1, so I'm going to round it down. Don't. You can't justify rounding that large of a difference. If you multiply this by 7, though, you will get very close to integer values. You'll get that this one is 7, and this one is equal to 8. This will actually come out to 7.98. That you can round up to 8. So the empirical formula is C7H8, and sure enough, toluene is C7H8. If you draw out toluene, you'll see that it's a methyl group attached to a benzene ring. Here's the 6 carbon atoms, here's the 7th, and there's 3 here, plus 1 hydrogen atom on each one of these corners. So it's C7H8. So there's your empirical formula for toluene.